All right, back from break. We have been looking at capacitors, and now what we want to do is we want to take these capacitors. We've been looking at kind of the properties in terms of building the capacitors and how much capacitance they will have if we build them with a certain area and a certain distance between the plates. Now what we want to do is actually take the capacitors that we've built and put them into a circuit. Now we've looked at circuits where we have just one capacitor by itself, but now what we want to do is take a look at capacitors where more than one capacitor is combined together into a circuit. So the circuit we have right here, we've got a battery, and we got some kind of a voltage set up. We're going to call this the voltage between point A and B. We're using the battery to maintain a voltage over here at this point. But then what we've done is between points A and B, we've connected three capacitors together. Not together, sorry. We've put them, well, this picture we have right here is referred to as a parallel circuit. The three capacitors are placed parallel to each other. Now the drawing shows them being parallel, but parallel means more than that. Parallel in a circuit, let's start at the positive terminal and do a walk around. When I get to this point right here, notice that it branches into three separate paths. There are three parallel paths that we can take in going from point A to point B. So that means that the capacitors, well, they're in parallel to each other, and when capacitors or any other devices are in parallel, it means that they're all getting the same voltage. So that's even maybe a more fundamental or more basic way to think about this. Capacitor 1 is going to get that full voltage, maybe it's 10 volts. And it's like taking the battery and connecting it here, and also taking the battery and connecting it here, and then the battery here is connected to each of the capacitors. So we can get three batteries, all of them 10 volts or whatever the voltage reading is on the battery, and connect each one of the capacitors individually. That would be the same thing as connecting them in parallel the way that we've done. So, and that's what it's saying here. It's saying these capacitors are in parallel, and we know that because we can look at the circuit and see that they're all receiving the same voltage. And one last thing to point out, these, the junction points here take us through each of the three possible paths, and that means that they're in parallel. Now what we want to do is we want to ask what would be an equivalent capacitor if we decided to take these three capacitors out and replace them with just one capacitor that in some sense had matching properties to it. What would that be? So let's take a look and see how we determine that. So here are capacitors in parallel. I drew the same diagram. I hope it looks the very same as the other side. And what we're going to do is start by identifying voltages for each of these and saying, oh, V1 equals V2 equals V3. I'm just going to call that V, where V is the voltage being provided at points A and B. Now, the voltages are the same, but that does not mean the charges will be the same, because the capacitances could be different. C1 and C2 and C3 could all have different values. In fact, I made some up. I'm just checking back to see if that's my doing or not. So here's capacitor 1, 2, and 3. I decided to have capacitor 1 with 10 microfarads, capacitor 2 with 20 microfarads, and capacitor 3 with 30. Now, I know enough about capacitors at this point. I could go in and solve for the charges. Capacitor 1 with 10 microfarads multiplied by the 20 volt battery is going to leave me with 200 microcoulombs of charge. That's how much charge will be on the plates of capacitor 1. And then charge 2 will be equal to C2 times V. That gives us 400 microcoulombs. And finally, capacitor 3 has even more capacitance. They're all getting the same voltage. That's 600 microcoulombs. So that's just an example of going in individually and calculating how much charge there is on each. Now, if I decided to do that algebraically, it would look like this. It would say Q1 is C1 times V, Q2 is C2 times V, Q3 is C3 times V, with the key feature here being that all the voltages match because the capacitors are connected in parallel. All right, now Q1 plus Q2 plus Q3, these are all different values of Q, but I could add them together and say that combined, they give me some total amount of charge. So in some sense, if I took these three capacitors out and replaced them with one that had the total charge Q, in some sense that capacitor would be equivalent to the three that we've looked at. So that's what we're going to do. We're going to define the Q this way. And then for that Q, what we can say is, well, if it's the sum of all these three, then it's C1V plus C2V plus C3V. I can factor out the common voltage. And that says that the charge, the total charge combined on all three of these capacitors is C1 plus C2 plus C3 times V. So that says that the expression in here, adding the capacitances together, that would give me the net capacitance in the circuit, or I guess I should really say this is an equivalent capacitance when capacitors are connected in parallel. Now that's pretty straightforward. I mean, if you kind of stare at the formulas long enough, you can see that that's what we've done here. We're going to get the 200, 400 plus 600 is going to give us 1200 microcoulombs, and the net capacitance now is 60. And that's the combined 10, 20, and 30 microfarads. So now we've replaced this circuit with the one here, and the charges are adding up. The voltages are the same. The voltages have not changed, and the capacitance is all added together. Okay, now for capacitors, it's kind of natural to add them in terms of, in parallel. And that's because if I think of these plates as being combined together, if I added up the area of the plates, 1, 2, and 3, that's kind of like creating a new capacitor with additional capacitance to it. So, now for capacitors, what's maybe a little more difficult to think about, not too much more difficult, but what would happen if I put them in series? Now, anytime we put devices in series, what that means is getting from A to B, I have to go through each one of those devices. They're all lined up right on the same path. There are no bypasses. There's no way to get around this. Getting from point A to point B requires going through each of the capacitors. So I have to think in terms of how much charge and voltage do I have here, how much charge, how much voltage do I have here, how much charge, how much voltage here. So let's take a look and see how the formulas are going to be similar or different from what we did when the capacitors were in parallel. So I put a switch in. I don't know if I put a switch on the other one. I always try to put a switch in. So here's a switch. I turn this on. The capacitors charge. Now, if you remember the picture we had for electrons going through a circuit, what that showed was when the circuit closes, where do the electrons start moving? And they move at every location in the circuit simultaneously. So it's not like we have to wait for capacitor 1 to charge and then capacitor 2 and then capacitor 3. They all charge simultaneously. Now they could have different, we'll find out in some later chapters, they could have different rates at which they're charging depending on their properties. But these are all going to charge together. And because they all have the same current going through them, for the same amount of time, they will all acquire the same charge. When we have devices, when we have capacitors in series, they're all going to end up with the same charge, assuming they started out with no charge. So we're going to say that initially the capacitors were not charged at all, started from 0, and then each of them charge together. They're all going to end up with the same amount of charge. I guess they do. Of course, they all charge at the same rate, actually, huh? They all charge together. Because we've got the same amount of current going through each one at each instant. Now what about voltages? Now if I get my voltmeter out, here's my voltmeter. I've got my 2 wires on my voltmeter because voltages are measured between 2 different locations. If I put my voltmeter across the battery, it's going to read the voltage being provided by the battery. If I put my voltmeter here, it's going to read the voltage across the battery. So the voltage from the battery is brought to this location by the wires. And so what's going to happen is V1, V2, and V3. So I'm getting out my voltmeter, measuring V1, measuring V2, and measuring V3. Well, V1 plus V2 plus V3 add up to V. This is a simple enough circuit. There's just a battery. It's direct current. The current's not going to oscillate back and forth. Once the capacitors are charged, they're charged. And adding their voltages will equal the total voltage provided for all 3 together. Now, this is going to be the case, that all the charges match. I'm going to use this formula of voltages and say V1 is given by Q over C1. That's just our standard formula for capacitance, flipped around. V2 is Q over C2, and V3 is 1 over C3 times Q. So following this formula, I can say V1 plus V2 plus V3 is equal to the total voltage. Now what I've done is I've defined an equivalent capacitance. The equivalent capacitance for capacitors in series is given by saying that Q divided by that equivalent capacitance will equal the voltage that we have over the entire set. So again, what we're going to do is we're going to take these 3 capacitors, we're going to remove them, replace them with 1 capacitor, and the idea is, well, the voltage that we have across this one will be the combined voltage, V1, V2 plus V3, and the charge that we have here will be equal to the charge that would have been on each of these 3 capacitors. So we get a formula here, and then we can factor out the Q's, because the Q's are all the same. And it says that the equivalent capacitance, 1 over C, where C is the equivalent capacitance, is equal to 1 over C1 plus 1 over C2 plus 1 over C3. So it's not too much more difficult, except that we're adding inverses. So it's going to be easier to make mistakes. We do have to be more careful about how we're managing this. So if I take the numbers that I had before, the 10 microfarads and 20 and the 30 microfarads, and plug those into the formula and solve for the equivalent capacitance, I ended up with 5.45. Now that's kind of an interesting number in that 5.45 is less than any of the capacitors individually. So what we're saying is, if I wanted to replace those 3 capacitors with 1 capacitor that had the same charge as each of the other 3 ended up with, I would actually use something with lower capacitance than any of the other individually. So that's kind of interesting. Now in this case, if we go in and we say, well, is the charge here equivalent to the sum of the 3 charges here? It's not, right? We're not going to be storing as much charge in this 1 equivalent capacitor compared with these 3. This would, here, each one would have individually a charge of Q, and the one we're replacing it with is just one capacitor with a charge of Q. But that's how we've set up and defined equivalent capacitance. It's so that the charge on this one matches each of the other capacitors that were in series. And that's the value that we ended up with. Okay, so it's a reduced value. Now what we can do is we can take these rules that we've come up with for the capacitors being added in series or being added in parallel, and we can combine those. So here's a circuit where I've got a battery here. I got a couple of capacitors here. I'm going to call this C2 and C3. At least they're going to call it C2 and C3. And then I have another one here that's C1. So how are we going to approach this? How can we combine these capacitors together? And we have to think of doing this sequentially. So I redrew the circuit. So here's the battery, and here is capacitor 1, and then capacitors 2 and 3. Let's go back and take a look at what they had drawn for us. If I do a walk around, just to see what things are like, I notice that here I've got C2 and C3 in parallel. Getting from this point over to here, I have two possible paths. Each one has a capacitor attached to it. And then once I get to here, I have to go through C1. There's no option. Now when I redrew this, I actually took C1 and moved it to here. But that doesn't alter the circuit fundamentally. I'm still going to have whatever voltage I had across C1 over here will now get moved over to the same voltage over on this side. Whatever voltage was here is going to remain the same in either case. So there is some flexibility with placement of these different devices, and that's something to keep in mind when you're solving problems. Often, redrawing the circuit will allow you to see it in a way you didn't see it before, and it will simplify the problem. So what we've got here is, here's the battery, here's a couple of capacitors. Now these are in parallel right now. If I look at C1, C1 looks like it could be in series with these once they're combined. So we're going to do this simplification, I guess, in two steps. What we're going to do is, first of all, combine these two in parallel to get an equivalent capacitance. And I'm going to call that C23. And then once my circuit looks like this, once those two capacitors are being combined, well then C1 is in series with C23. It was not in series with C2 and C3 individually, but once 2 and 3 are joined together, it's in series with those. And so then I can combine these in series, and I'll say the value I get here is C123. Okay, and I've put plus and minus signs on the sides of the capacitors. So to designate the way that they're going to charge. So for the parallel case, I'm going to take C23 and say, well, that's equal to C2 plus C3 according to the formulas that we just derived. So that was easy enough. That's my first step. Now the second step is a series combination. So I'm going to have to take 1 over the combined capacitance is equal to 1 over C1 plus 1 over C23. Now a little algebra on that gives me 1 over C123 is equal to C1 plus C23 over C1 times C23, and then I flip the whole thing over to get C123. So that's it. What we've ended up doing is being able to get a combined expression for C123. Now, let me see if I've got that right. I think this needs to be a 2-3. Let me see if I can get that corrected on the slides that we actually send out. Maybe I'll get that corrected and reposted. This one needs to be a C23 right here. So what we can do from that point is, here's C1. Now C23, if you remember, was C2 plus C3. And then down below 2, that should be a 2-3. That's going to be C2 plus C3. So the formula works out to be this. Now, and then I plugged all the numbers in and I got 8.33 microfarads. So the values given, oh, were they 10, 20, and 30? I think I'm just doing that, right? They're only doing it, yeah, they're only doing it algebraically. So I'm putting in the 10, 20s, and 30s just because I think it's good practice to go in and plug some numbers into these formulas and see what we end up with. Okay. Now that was a fair amount of algebra to go through. It turns out that it's easier if we, it's often easier if we do these problems, set them up a little differently. Okay, so I'm going to go ahead and move on to this next example. But before I do that, just let me say, here I did everything algebraically, but I could have started plugging numbers in sooner. Rather than carry out the entire calculation algebraically and then putting numbers in at the end, I could have started putting in, like for C23, I could say C23 is 50 microfarads, and that often works well. I know I'm always saying do the algebra first, but in some of these problems the algebra gets complicated. It's easier just to put some numbers in along the way and solve for, say, C23 first, for example. Something to keep in mind. All right, if we try another example here, charge and voltage on a couple of capacitors. And I guess 1, 2, 3. Oh, I guess this is their picture, right? This is their intermediate picture. They have the same effect. Right. And so example 24.6 is really just an intermediate picture of what we just did. And then what we can do is, let's do a table this time. So I'm actually going to go all the way back to that picture and then say, is there a way I could just set this up kind of systematically? And so the way that would work is I'm going to write down C1, C2, and C3. I'm going to make some columns. And then for capacitor 1, 2, and 3, I'll write down what the capacitance is, 10, 20, and 30. And then I'll write down what the charge would be on each one. And then I'll write down the voltage. And then I'll also write down the energy. Now the energy formula is right here. We'll come back and see where that formula is coming from. But in any case, what I'm doing this time, instead of doing all the algebra, is I am saying that C23 is C2 plus C3 and adding them together and getting 50 microfarads. And then I'm taking the inverse of this and the inverse of this, adding them together, taking an inverse, and that gives me the 8.33. So these are numbers that we calculated along the way. The only new item that I've added to this example is to introduce a voltage. So I decided to put in 60 volts. I don't know why. So 60 actually is divisible by a lot of numbers, so putting 60 in a lot of times, it could simplify some of the calculations that we have to go with. So anyway, what I can do is I can put in 60 volts. Let's say I have a 60 volt battery. And what I can do then is I can say, if I combine this all into capacitor 1, 2, 3, then the charge on that capacitor should be C123 times the voltage. That would be 500 microcoulombs. Now what I can do is I can place that in my table that I've put together. I've got the combined capacitance, I've got the net voltage, and from that I can calculate the charge. So what these columns consist of, 1, 2, and 3, are the actual capacitors themselves. And then 2, 3 is what I would have once I've combined 2 and 3 in parallel. And 1, 2, 3 is what I'll have when I've combined these in parallel, and then taken C2, 3 and C1 in series to get the 8.33. Now, since for each column, Q is equal to C times V. And that means that in a column, once I have 2 entries, I can calculate the third one guaranteed. So in a problem, for example, what might be given is, let's say they give us C1, C2, and C3, and they give us the overall voltage of the battery. So what I can do is I can complete row number 1, the row at the top, to get the net equivalent capacitance, use this formula, Q is equal to CV, to get the charge on that equivalent capacitor, and then I can work back through the table. What I can do is say, well, if C123 is at 500 coulombs, so is anything in series. So that says 500 microcoulomb, the C23 and the C1 will have the same charge as C123 because they're in series with each other. And I wrote that down right here. Now, to see everything going on, it's probably useful to go back and see what some of these intermediate pictures look like. Okay, so this is what happened along the way. C23 and C1 are in parallel. All right. Once I have these entered in, then I can get the voltages. So the next step is to say, well, I know what Q1 is now. I know what Q23 is. I can solve for V1 and V23. And that's going to give me 50 volts and 10 volts. So I know how the 60 volts divides up. Now, the 60 volts is dividing into 10 volts here and 50 volts here. But this is still a combined capacitor. This can be divided up by parallel. And it says that the voltages on C2 and C3, the next step here is to say V2 has the same voltage as V3, as capacitor 3, and that's going to match the V23. So the 10 volts we have here gets placed here and here, and from those we can calculate the charges. So I've tried to step through this step by step, very systematically. What's not here is a picture of all the intermediate circuits. So for those, you're going to want to go back to those earlier drawings right there. Okay. Now the energies can be calculated, and we'll see where these formulas come from, as 1/2 Q times V. 1/2 Q times V will tell us how much energy is stored in the capacitor. Back in chapter 23, we show that the charge times the voltage represents a certain amount of energy, and the formula we had was just Q times V. But capacitors, when they charge, they don't maintain a constant voltage during the time when they're charging. So a little bit of charge shows up first, and then a little bit more, and then a little bit more. And as a result, during the charging process, we only have a net energy storage of 1/2 QV. But what I've done here is I've calculated that for each one of the capacitors. So for capacitor 1, 2, and 3, I've calculated the energies. Now I've calculated energies here too and added them in, but these don't correspond to actual capacitors, but I can still do that. And the equivalent capacitors will follow the same rules that we've had for the actual capacitors themselves. All right. So this is a good example in adding capacitors in series or in parallel. Okay, here's another example with these capacitors. Here what we're going to do is we are going to connect these. We've got a 24 volt battery. I've got capacitors here, capacitor 1, capacitor 2. Those are in parallel compared with each other. So what it's saying is I have two capacitors. They're connected in parallel to a 24 volt source as shown in the initial configuration We're going to charge those, and then we're going to take those out. We're going to disconnect them, flip them relative to each other, and reconnect their terminals, or reconnect their plates. Now, when we charge these, this one's becoming positive. This plate is positive, this one's negative. This one is positive and this one is negative. When I disconnect them, and I go ahead and get some lunch or something and I come back and the charge is still there. So now I'm going to take these and connect them so that the positive plate on one matches with the negative plate on the other one. What's going to happen? Well, some of the charges will cancel each other out. In fact, if Q1 and Q2 were the very same value, if for some reason the capacitance are the same, they're not in this example, but if the capacitances were the same, then the charges would be the same. If I disconnect those and reconnect them oppositely, all the charge would cancel out. But it's not all going to cancel out. Capacitor 1 has more capacitance than capacitor 2. And so I'm going to end up here with different amounts of charge. So what we'll do is we'll find out how much charge is left on this side. Now the charge that remains is going to get divided between capacitor 1 and capacitor 2. Everything we calculate for this works the very same with the lower plates, except the signs will be reversed. So let's take a look and see how this works out. It's a good conceptual problem for thinking about how these capacitors work. Here was the initial setup with my 24-volt battery. For capacitor 1, which has 2.2 microfarads of capacitance and a 24-volt voltage source, that's going to store up 52.8 microcoulombs of charge. Now that's a positive amount on the positive plate and the negative amount on the negative plate. Capacitor 2 has a different capacitance, 1.2. Multiplying that by the voltage, I get 28.8. So I've got 52.8 coulombs, plus microcoulombs, plus and minus on these plates. And then I have 28.8 plus or minus on these plates. Now what's going to happen is when I disconnect them, these are the charges that I'm going to have stored. But notice that when I reconnect them, I'm going to have the 52.8 is going to line up with the negative 28.8, and that will cancel out a good portion of the charge. So what will happen then in this case is that these plates will remain positive. So let's say that C1 is oriented the way it started out, but C2 has been reversed. So we took out C2, we flipped C2 over, so its plate here was negative, and then the negative plate from here will cancel out some of the positive charge here. So we're going to be left with some combination of charge, and that's going to be Q1 plus Q2. Now the same thing's happening on the negative plate, but with opposite signs. So at equilibrium, when I flip these and connect them, what will determine how the charges arrange themselves between capacitor 1 and capacitor 2, and at equilibrium, the voltages will match. So that's going to be my principle that I'm working from to decide when these capacitors reach equilibrium. So what we can say is if the voltages are the same, that the voltage on this side matches the voltage here, then Q1 over C1 is equal to Q2 over C2. Now what I can also write is that charge was conserved, meaning Q1 plus Q2, the combination of those two charges, has to equal Q1 minus Q2, and Q1 minus Q2, I just called it little q, and that's 24 microcoulombs. Okay, so I know what Q1 plus Q2 have to add up to be 24, but they also have to be in this ratio. So let's get those two formulas written down and see how we're going to combine those. So Condition 1 says that the voltage on side 1 matches the voltage on side 2. Condition 2 says that the combined charge was conserved. So with this being 24 microcoulombs. Now what I can do is I can do a substitution. I can say that Q2, using equation 1, I can say that Q2 is equal to Q1 divided by C1 times C2. So this expression right there, that's the equivalent of Q2. So now I've got, instead of 2 equations, 2 unknowns, I have 1 equation, 1 unknown, and it says that C1 times Q1 plus C2 times Q1 is equal to C1 times 9, and that leads to this set of equations, right? It's not 9, I'm sorry, that's total Q. Yeah, the total Q's look like 9. I'm having a bit of an issue with that. The little Q's don't work as well. But in any case, what it's telling me is that capacitor 1 will end up with this portion of the total available charge. And capacitor 2 will end up with this portion. So C1 over C1 plus C2 compared with C2 over C1, I can solve for those. Capacitor 1 will end up with 0.647. About 65% of the charge will end up on capacitor 1, and about 35% will end up on capacitor 2 based on the algebra that we've done. So putting those numbers in, it says that Q1 is going to end up at 15.5, and Q2 is going to end up at 8.5, and if I add those together, they are 24. So that's a pretty interesting problem to take a look at here. Okay, here's the energy formulas. The energy, we said, stored in a capacitor can be written as 1/2 Q times V. We can go through and derive that. Now, since Q is equal to C times V, the energy could be written this way. Or because V is equal to Q over C, I could also write it as the lower fashion. And this is pretty standard when we start looking at circuits and devices in circuits. Often, for the same quantity that we're trying to solve for, there could be 3 different ways, 2 or 3 different ways that we can solve for it. So it's fine. This definitely works. And as I was saying, I don't think I'm going to go through the details of this. If you guys want to look at it, you're welcome to. But what's happening here is there's a charging process. And as a capacitor charges, its voltage is increasing at the same time the capacitor is charging. And that means the first charges that come in don't require as much energy storage as the later charges. And as a result, we end up with this factor of 1/2. Okay, now here is here's a camera, right? And so this is a flash for a camera, and it's got these big capacitors inside here. Got quite a few capacitors. This is a capacitor, that's a capacitor, that's a capacitor. They all look like capacitors. There's a really big one there, and what we're going to do is use that capacitor to release a lot of current in a very short time, and that will make the camera flash. So that's how we're going to get the flash out of this. So let's put the numbers in and see what it comes up with. It says that the camera flash unit is storing energy in a 150 microfarad capacitor. Ooh, but it's storing it at 200 volts. So there's some kind of voltage booster taking place here, some kind of a transformer or something that's giving us a voltage boost. So to calculate this, what we can do is say, fine, it's 200 volts, don't go near that battery, and 150 microfarads of capacitance. The charge then that we're storing is 30,000 microcoulombs, which, since it's 30,000, I converted that over into 30 millicoulombs. Now my energy formulas, I can use any of these. All 3 of those formulas are equivalent to each other. Since I know the voltage and I know the charge, I'm going to use this one. You know, actually, I guess with the information given, I could have just started out and done this, but I was interested. Did they actually ask for this? I was curious how much charge is stored. No, they actually didn't ever ask for that. But, you know, curious. So this is how much charge we've got. This is the energy stored. It's saying that we've stored about 3 joules. Now, it says that all of this energy can be released very rapidly through the flash bulb in 1/1000th of a second. So to calculate the power that that capacitor is providing, I can take the stored energy, 3 joules, and on average, this is kind of an average power, it's saying that that energy is released. I can divide through by the time, and during that 1 millisecond, on average, that's providing 3,000 watts. So that's probably providing energy at a faster rate than a battery would be able to do. So a battery would not be able to release that much energy that quickly. So what we've done in the camera is we have a battery, we close the switch to charge up a capacitor. You know, if I'm charging the flash on a camera, maybe I hit something that says prepare flash or something, and so the capacitor charges, and then we open this switch up, and then whenever I hit the shutter, the other switch closes, and all of that energy dumps into the flash very quickly. So that's, you know, one of the applications for the capacitors. Okay, so this is a slide. I might take this one out, actually, that says be careful with electricity. Okay, so be careful. This is an energy density formula. And this is going to be useful. We're going to use it right now for capacitors, and then we're going to also use it later on, keeping track of how much energy there is in electric fields in general. And so when we have electric fields anywhere, we can actually do energy bookkeeping by saying the field squared divided by 8 pi k gives us an energy density. Now, energy density has units of joules per cubic meter. In order to actually find out how much energy is stored, I can take the energy density and I can multiply by the volume. So the way it would work is this. Here is the total energy stored in a capacitor. That's 1/2 QV. The charge that we've stored is equal to 1/4 pi k E times A, according to Gauss's law. And then the voltage would be E times D. So it says that the total energy that I've stored in a capacitor, if I combine everything together, is 1/2 times 1/4 pi k. That gives me 1/8 pi k. And then I've got a factor of ED and a factor of EA. What I can do is I can bring those two factors of E together. That gives me 1/8 pi k E squared. The area multiplied by the distance, this is my capacitor here, if I take the cross-sectional area multiplied by the distance, that's going to give me the volume. So what I've done is I've showed that the energy can be calculated by using an energy density formula. The capacitor has an electric field inside, and by squaring the electric field and dividing by 1/8 pi k, that's telling me how many joules I have per cubic meter, and then multiplying that by a volume will give me the total energy. So it's an energy density. So that's a handy concept to work from in many situations. Now, this example, and I think I'm going to move through this one too. I don't think I'm going to go through this. So this is a sphere that's going to be charged just along the surface, and it's showing how much energy it's going to take to bring in each additional piece of charge. And in the end, we can calculate how much energy is stored there. But I think I'm going to move on to some other examples here. These are interesting. They're calculating the energy of a charged sphere in 3 different ways. But I think I'm going to, 2 different ways. I thought I had, okay. I'm going to move on. And so Here's another example of capacitors. So here are some emergency technicians, emergency medical technicians coming, and they've got, maybe they have the paddles out, so they're able to use an electric discharge from capacitors to kind of jumpstart the person's heart in this example. All right, the last topic we want to look at in the chapter is looking at what we call dielectrics. Now, dielectrics are insulating materials that are used within a capacitor well, for a couple of reasons. They provide structure for the capacitor, and then what they also do is they increase the capacitance. So this is a pretty nice feature. So here is a capacitor that we've been looking up until now. It has charge on it. I'm going to call it Q naught, and the Q naught is equal to C naught times V. Well, if I put dielectric material inside, the capacitance goes up. And we'll take a look at the reason in just a minute. But you can think of this dielectric constant, big K, as just some kind of a material property. I can look that up in a table. And it has to do with the polarizability of the material. So I can take that dielectric constant, multiply by the original capacitance, and it gives me a boost. K is some value bigger than 1, and so with the dielectric I'm going to be able to store more charge using the same voltage. So I'm going to connect the capacitor to the very same battery. Here's what's going on behind the scenes. If I just have the two layers, I've got an electric field set up between the two plates. Now, if I put some material in that is able to polarize, meaning that when I put the material in and the surrounding plates become positive and negative, the material inside, the electrons get pulled to one side and the nuclei get pulled a little bit to the other. It's not like they separate, but all the electrons shift just a little bit. And that means that within the material, we can think of individual atoms as having kind of a negative side and a plus side. That generates an electric field of its own, which opposes the electric field being set up by the plates. Well, the plates interpret this as, well, we don't have enough charge stored up yet, and so they can store additional charge. It's kind of a nice feature that the capacitances go up by putting materials inside. Okay, and this is kind of describing what's going on at the molecular level. Here's a table from the textbook showing that if it's just in a vacuum, the dielectric constant for a vacuum is defined to be 1. But if you put it in air, even air itself has a little bit of polarizability. It's not much, right? It looks like 6 parts in 10,000 or... yeah, so it's not much. And then paraffin, polystyrene. Look at this, if we get strontium titanate, that polarizes in a way where we get a boost of 300. So the capacitance could go up 300 times by putting just a thin layer of strontium titanate inside there. So the layer thickness isn't important here. It's just enough so that that polarizability effect can occur, and that can be a very, very thin layer. Okay, here's a couple of experiments, it's saying, that we could think about doing with these capacitors once we have put the dielectric material inside. So one of these says that, the first one, the one on the left here, says we haven't put the dielectric in yet, but we're going to do that. Now, one of the ways we could do this, in the first example they're talking about here, a capacitor has been connected to the battery, we've stored a certain amount of charge, and the capacitance is given by Q naught over V naught, which gives us the standard capacitance. Now, what happens if we put a piece of dielectric in here? Well, from what we were just talking about, the amount of charge on the plates can increase by a factor of whatever the dielectric constant is. And we can establish that just doing a series of experiments. And so the charges go up, And that means that now the capacitance has gone up by a factor of k, because the amount of charge going up has increased by a factor of k. The amount of charge stored in the capacitor has gone up by a factor of k with using the same voltage battery. Now, a second experiment we could try here would be to charge the capacitor, but then disconnect it. Now, when I left it connected to the battery, that meant that the battery could bring charge back or supply more charge, and the voltage would stay the same. But in this example, we've disconnected it, and that means this charge is isolated. It can't go anywhere. There's no battery to provide more charge or to pull charge back. So it's the voltage that will be affected this time. So now when we put the dielectric in there, the charges actually stay the same, but the capacitance has gone up, and as a result, the voltage between the plates goes down. So we're just, just some examples thinking of, in a laboratory, how could you charge these capacitors and then get out a voltmeter and do some measurements to establish what the dielectric material is doing. Okay, one last example here. It says that we have some parallel plate capacitors. We put some dielectric material into here. It's got a K value of 3.4. This is at 100 volts. That's a lot of volts. And it has a distance between the plates from one surface to the other. That's 4 millimeters. They want to know, what will the capacitance be? Find the capacitance, the charge on the capacitor, the electric field, and the amount of energy that's being stored. So let's take a look at that. So let's think of this two ways. Let's first of all think of it as no dielectric present. With no dielectric present, the capacitance that we solve for here works out to be 88.5 nanofarads. Now when I put the dielectric in, it says that I'm going to get a boost of 3.4, and that says I'm up to 301 nanofarads of capacitance. And since I have a voltage of 100 volts, that's going to result in 30.1 microcoulombs of charge. So the charge here is going to be treated as being constant. So what we're going to do is, I've got this much capacitance with the dielectric in place. I can calculate the energy stored, and the energy stored here, using 1/2 Q times V, is going to be 1.51 millijoules. So check all the numbers on these. And the electric field then, I can calculate as V over D, and that's 25,000 newtons per coulomb. Now, what happens when I remove the dielectric? So in part B, they say calculate all these numbers with the dielectric in place, and then carefully pull the dielectric out. So we've disconnected the capacitor, meaning that the charge is going to be the same as it was before. The charge has nowhere to go. But when we remove the dielectric, the capacitance of 301 nanofarads reduces back down to 88.5 nanofarads. And that says that the voltage then is going to, end up going up by a significant amount. So again, the voltage is going to be given by Q divided by the capacitance, and it didn't take so many volts to store that charge with the dielectric in place. When the dielectric was there, I was storing all that charge with 100 volts. But now that I've removed the dielectric, it's requiring a higher voltage to store that. So if I get my voltmeter out and measure it, that voltmeter is going to read a higher value. Now, when I solve for energy then, what I find is when I remove the dielectric, there's a lot more energy. There's like 3 times as much energy or more being stored. There's actually 3.4 times as much energy being stored. Where did that energy come from? And I actually have to forcefully remove the dielectric. The dielectric wants to stay inside there. So I have to do work by pulling it out of that region. And when I do, the voltage goes up and the electric field jumps up to 85,000 newtons per coulomb. So kind of interesting that you can take these capacitors and either putting a dielectric in or pulling a dielectric out involves energy transfers. It could be that we have to invest energy. We have to transfer energy in by forcefully pulling the dielectric out, okay, as in this example. Okay, I'm going to stop there. I think we're at time. So that wraps up chapter 24. We are looking pretty good. We've made it through this first chapter looking at circuits. Really, we're going to get more into circuits in chapters 25 and 26. Also, we got a couple more chapters coming up with that. So you guys have any questions at all, stop by office hours. Let me know. We can get all those questions answered, I think. So definitely stop by.